Hi, everyone. My name is Carrie Ann Wilson. I am a first year PhD student at the University of Michigan. Welcome to the MTV Summer School. Today, Ethan Schneider will be giving us a talk on the physics of neutrons. Ethan is a first year PhD student working with Professor Sarah Pozzi at the University of Michigan. Um, Ethan earned his Bachelor's of Science in 2023 from the University of Texas, San Antonio in physics. And his work here focuses on characterizing organic glass scintillators and neutron detection. So thank you so much for attending, and Ethan, take it away.
All right, hello everyone. Let me know if you have any issues hearing me or if anything cuts out. All right, so I'll be going over brief introduction over the physics of neutrons. So for just an overview of what we cover today is that we'll be going over various neutron sources, an overview, as well as the overview of how they work, as well as a few examples on their applications and a few example problems for us to look at. So first and foremost, the neutron is one of the main nucleons within our nucleus, and it has a mass of around 938.56 MeV per c squared, or around 1.0086 AMU. So this convention of MeV per c squared is it's a very convenient way of working with mass at this scale, as most of the energies we're working with is on the EV to MeV range, and by expressing it in terms of E equals mc squared, we're able to make this math a lot easier. Note that the mass of the neutron is very similar to that of the proton, but significantly higher than the rest mass of the electron. So the neutron, its defining feature of that being no charge, makes it very useful for its interactions with with matter. Since it has no charge, it will pretty much pass by the electric field almost all the time and interact directly with the nucleus. And that allows us to do exciting science with that. Whenever we look at neutrons, we tend to classify them based upon their energy, and they have around two to three different forms we usually consider. We have the thermal neutron, which is below 0.025 eV. This just corresponds to, well, and we'll get to this later, but it corresponds to the energy of a neutron that will be captured by cadmium at a certain thickness, around 1 millimeter. Anything between this and 1 MeV is considered a slow neutron, while those above 1 MeV are fast neutrons. And this is the most common neutron energy we're looking at today. So whenever we have, in previous weeks, we've talked about gamma sources, and our common source of gammas are from the de-excitation of a nucleus. So following a beta decay, cesium-137 can exist in an excited state, barium, as seen on this diagram here, where the star indicates an excited state. Around 93.5% will decay into the excited state, while a few will directly decay into the ground state. In this excited state, it wants to return to a ground state and release a gamma ray that corresponds to that energy difference. However, we don't see a similar situation with the neutrons. So our neutrons have a very high binding energy to our nucleus. And because of that, we don't ever have situations where a nucleus will reject. We don't tend to have instances where a neutron will be rejected from the nucleus to get to that point. So on the right, you can see the different average binding energies per nucleons, and it peaks around at iron, or 56, and decreases as we get to our actinides. So as you can see here, the average binding energy is much higher than the 622 at keV, where we have average binding energies of around 7 MeV, 8 MeV, or even higher to 9 MeV with iron. So one way we can get neutrons is through an alpha capture reaction. So here we can have a actinide or an alpha emitter such as plutonium, which will decay with and release an alpha particle, which is simply two protons and two neutrons and clumped together. And this can be captured by a beryllium or any other, by plenty of other targets. These targets will then absorb this alpha particle and then release a neutron following this. For the average energy of this particular reaction is around 4.5 MeV. So there's plenty of other alpha capture reaction sources. So for instance, we can use different kinds of actinides. For instance, we have plutonium-238, as well as americium-241, which will then decay into two different isotopes of uranium. These alphas can then be directed upon a beryllium source, which will then absorb that alpha particle and then produce carbon-12. Carbon-12 and our neutrons. In addition to this, we can swap out the actual alpha source, well, not alpha source, but the target of this alpha particle for lithium, which will then produce a much lower energy neutron. So in this case, we have we can tailor our sources that we have on hand to the type of measurement we want to do. And for here, just note that since the alpha particle is a heavy charged particle, it will be attenuated pretty quickly. So whenever we make these kinds of sources, our plutonium and our alpha target have to be incorporated in the same area, so the alpha particle doesn't lose all of its energy before hitting our target. On the right, you can see an energy spectrum of our neutron energy for an AMLI source. So here's also another descriptor of that plutonium beryllium reaction. On this slide, we can also see that, so note that our energy spectra will be very different whenever we look at so note that it's not monoenergetic. So we don't just have a single 4.5 MeV peak. We have all these different energy states that correspond to the different energy states that carbon-12 can take. So another neutron source is our spontaneous fission sources. So this is whenever we have a nucleus like Californium-252 or plutonium-240, it primarily will decay by alpha emission, as seen in the previous slides. However, there is a small chance with californium, it's 3%. With plutonium, it's even lower. So 3% of the time, it will decay by fission event. So these fission events will produce not just one neutron, but will produce many neutrons per fission. And because of that, we're able to get a pretty high neutrons per second per gram. This just gives us an idea of how little of a source we need to get good statistics in our experiments. So, and the average energy of this particular reaction is 2 MeV. However, the most likely energy will be around 1 MeV. Plutonium-240 is very similar. However, it just has a much lower chance of spontaneous fission. So in most cases, we can assume when you're working with a source, you'd say it's primarily alpha decay. Because that lower chance of spontaneous fission, we get a much lower neutrons per second per gram. However, we have a very similar average energy. We also have photoneutron sources. So here we have a sodium-22, which will decay by beta decay, and will have an excited neon-22 atom. Here it will decay by releasing a gamma, which can then be captured by a beryllium target. So here we have a photonuclear reaction in which that photon represented here reacts with our beryllium target, which will then release a neutron. So here we have the composition of the source is very important, where we have our gamma ray source and our beryllium surrounds it. And this is just done to increase the probability of interaction between our gamma rays and our beryllium target. So another form of interactions we have are fusion reactions, in which here we have both DD and dt, where D represents deuterium, which is an isotope of hydrogen, and tritium, which is an isotope of another isotope of hydrogen. Here we have a accelerated plasma beam of hydrogen, which interacts with our target of deuterium. This will then produce helium-3 as well as a bunch of neutrons with an average energy of 2.45. So similar energy range of our spontaneous fission. In addition to this, we can also have DT reactions, which has a much higher average energy. So here we can, so this is once again another neutron source where we can tailor our energy to what our experiment calls for. The reason we have this plasma beam is to overcome the energy threshold for this reaction. For our DD reaction, it's around 4 keV, and for DD, it's around 7 keV. You can see that in our bottom left figure, which gives us the cross-section information with respect to energy. And cross-section is for now, we can just think of it as similar to that of probability of interaction or probability that we're going to see this reaction take place. So obviously, if we want this kind of detector and want to produce those neutrons, we want a higher cross-section. On the bottom right, you can see an actual cross-section of these detectors. Well, not detectors, this neutron source. This is from a group out called SHINE. And right here, we can see that plasma beam interacting with our target deuterium and producing those neutrons. Note here, what we're seeing is the excited gas and not the neutrons themselves, since the neutrons are invisible. So these are just the excited gas particles here. So here we can talk about different scattering of our neutrons. We have both elastic and inelastic scattering, which should sound familiar from any introductory physics you might have taken. Where we have elastic scattering, we have where kinetic energy and momentum are conserved, and inelastic scattering, where only momentum is conserved. So the elastic scattering, it's a very classical scenario in which we have a neutron, which will be scattering off hydrogen, producing a scattered neutron and a scattered hydrogen. Here, our main things that are interested in knowing is that angle of scatter, as well as the energy of the recoil, E sub r, which is given by the hydrogen. And from here, we can figure out the energy of the neutron. So an E sub n represents the energy of the incident neutron. Here, we have the energy of our recoil atom is given by 4 times A, which is the mass of our target, divided by 1 plus A squared, times the cosine of the angle between the axis that interacts and the recoiled hydrogen. So here we can do a quick example problem where you figure out the maximum and minimum recoil energies of this scattered neutron and recoiled hydrogen. So note that the incident neutron is going to have around 2.45 MeV, and here we'd have all the information to solve for E sub r. So I'm going to give you guys a good 1 minute to look over this problem, and you can post your results in chat. I'll give you about 1 minute. All right, so if you have any, for those who worked out the problem, you can post in chat, or I'll just go ahead and go through the answer. So here we have our maximum would be given by our cup, in which the situation in which our scatter angle is just 0. So here we have, since a is equal to 1, we plug that in for a, multiply it by cosine of 0 times 2.45, and our maximum recoil energy of hydrogen is a full energy transfer from the neutron. So the neutron will transfer all this energy, and the other situation where we have where theta equals 90, our energy of the neutron, well, we'd have the exact opposite of that, in which there's no energy transfer. Sorry. The minimum energy of our recoil would be given by the 90-degree scatter case, in which it has no energy given to it by our incident neutron. And this is to be expected. As our E sub n will be 2.45. Our other case is inelastic scattering, in which we have the formation of a compound nucleus. So here our neutron will come in and interact with our nucleus and form our new nucleus in an excited state. This new nucleus will then emit a neutron, as well as recoil, as well as produce a gamma ray. So here it's a much more complex problem, and for that reason, we'll be not doing an example problem based upon that. So this kind of reaction has a threshold associated with that. The threshold energy for this reaction is given by the mass of our target plus 1 divided by A, multiplied by E sub 1, which is the first excited state. So this excited state of the nucleus varies greatly as we go up the periodic table. Our lighter elements will have a much higher first excited state, as opposed to our heavier nuclei. So because of this, it's much harder for us to have these reactions with our lighter nuclei. And this doesn't occur at all for hydrogen, but it's very important for our uranium reactions. So now we can look at absorptions. So the first one we'd have is our radiative capture, in which we have neutron absorption and then de-excitation. So here we can have the neutron absorption of plutonium-240 or 239. So this is something you'll see a lot whenever you have shielding. However, it's also used in indirect detection techniques such as activation foils. So here, for an activation foil, we can have a foil that's placed in the presence of neutrons, which it will have these kinds of reactions in which it will absorb neutrons and then become activated. In that case, it will then slowly release energy through the form of gamma rays. In this case, with an activation foil, we can use elements such as indium, which has a pretty short half-life of about 54 minutes, and gold with a half-life of 2.7 days. And once we have these kinds of foils, we can place it in proximity of another detector and observe and get a good idea of the dose of neutrons that this foil received by just measuring the amount of gamma rays that are produced by it. So we can also use cobalt, which has slow neutrons, and magnesium for fast neutrons. So just remember, the reason why we would use different metals is that different elements will have different cross sections, and those cross sections determine what the rate of which those reactions are occurring. So we also have capture transmutation, where we have the absorption of a neutron and then it can de-excite by emitting a particle, which is not a gamma ray. So here we can have a neutron upon helium-3 and neutron upon lithium-6. So here, these are two very important reactions that in our field, as helium-3 and lithium-6 are used in different detector types. The reason why they're pretty useful is that these reactions have a very high Q value associated with that. That just means the energy produced by this reaction. So for instance, helium-3 has a Q value of 0.76 MeV, and lithium-6 has a much higher Q value of 4.78. So this gives us a high energy particle that we can easily detect as it's a heavy charged particle. So within a helium-3 detector, this is very useful as it produces those high energy particles and it has a very high cross section for thermal neutrons. So we can have a pretty efficient detector for neutrons and neutrons only. So this is just a reiteration of what I was just previously talking about, that we can use it to detect neutrons, but note that we're not detecting the neutron itself, we're detecting the charged particles that are produced by this reaction. Here we can also go over our neutron product energies. So if we have a thermal neutron, we have a neutron that has an energy much lower than that of our produced our alpha particle and hydrogen that are produced by this reaction. So our thermal neutron is less than 0.025 eV, which is many orders of magnitude than the MeV scale of our hydrogen and alpha particle. Here we can work out, given the two masses of our particles and for the first energy, or the incident energy, we can use that to calculate the maximum minimum energies of the reaction products. So I'm going to give you guys 5 minutes to go over this by yourselves. And if you have any questions or answers in chat, please respond there. Looking at the chat, I noticed that there was a question on the A and on what I meant by that when I said it was always given. And whatever I mean by saying that's always given is that we usually have a good idea of what the target, when we have these detectors, we have a good idea of what our neutron is actually interacting with. So since it's always given, we know that we have either if we have like plastic, it's probably made of if it's made of hydrogen carbon, we know that, or if it's a lithium atom, we'll know that mass as well. Okay, I'm going to give you guys 2 more minutes. Let me know if you need me to go back a slider or if there's any other questions you guys have about the framing of the question. All right, I'm going to go ahead and start going through the how you actually solve this problem. So first we have our energy balance in which we have the incident neutron energy E sub n plus Q, the energy produced by the reaction, and that should be given equal to the energies of our two products, our alpha particle and the hydrogen. Here, since we know that we have a thermal neutron, we can assume that E sub n is equal to 0 relative to these other products. We can also do our momentum balance, in which we have our mass of our hydrogen times the velocity of hydrogen should be equal to the mass of our alpha times the velocity of our alpha. Here, we can now plug in our substitute. We can convert this expression into the one below it through E equals 1/2 mv squared, which is our classical expression for energy or kinetic energy. Here, we just multiply E by 2 and m and take the square root of that, and that expression will now be equal to mv. And that's how we get this expression here, where the square root of 2 m of our hydrogen times energy of a hydrogen is equal to the square root of 2 m sub a E sub a. Now we have our two products are both isolated on both sides, and we can multiply. Now we have both these sides, we can square both these sides, and we have 6 m sub n E times hydrogen is equal to 8 m sub n times the energy of the alpha. And now we can express the energy of a hydrogen with respect to energy of our alpha here, and we just cancel out our mass of our neutron terms. So now that we have an expression for the energy of our alpha with respect to the energy of hydrogen, we can plug that into our original equation for energy, which we have our known value of Q. And now we have a expression for energy of alpha. We can solve for both the energy of our alpha particle, 2.05, and the energy of our hydrogen, 2.73. So notice some other questions in chat. So the difference between the thermal and neutron and the slow neutron is simply the energies. That thermal neutron is below around 0.025 electron volts. And the slow neutron is simply above that and between 1 MeV. Yep, so Q is that value. So whenever we have these kinds of reactions, whenever we have this reaction, it's similar to that of a chemical reaction in which you can release energy. That is that Q value. So that's the energy produced by this particular reaction.
Here, and I can cut in a little bit there. But it's the binding energy of those nucleons when it like splits apart and creates that. So you can calculate this by doing MC squared for the um, reactants in the products and doing that math, and then you can find it that way.
Yep, and where we have the difference in the components by themselves and the components of the actual nucleus is going to be different, and that difference in mass will give us that Q value. And for the question, does and there was another question on does the nuclear fission process go on and on in terms of neutrons released? And I'm not sure if that's a question about whether the process is self-sustained, but in some cases it can be, but that depends on a variety of factors such as the density of your system and the neutron multiplicity uh, of those processes. So we also have induced fission, which in this scenario, we can have the absorption of a neutron, which will excite our nucleus, and then it can split our nucleus into two different charged particles. So here we have our induced fission. So we have this is probably the most familiar one, the most familiar process in the public's eye, as this is our primary way of having energy production. So here we can have a neutron that interacts with a uranium nucleus, will then excite this uranium, and this will produce our two heavy charged particles. So note here that we just have a barium and krypton atom. However, this process has a lot of variation within it. So the charged particles produced by this particular isotope will vary from fission event to fission event. You can see that here where we have a large distribution in which, one, you can note two things, that we have a large number of variation in our mass number, which just corresponds to different heavy charged particles that are produced by this reaction. Also note that it's not symmetrical. It has a double dumbbell shape in which we have our heavy charged particles in the region around 90 and around 140. Those are our favored ones, which you can see with barium 144 and krypton 89. We have this dip in the middle where this symmetrical fission, where if we were to have a initial isotope of 235, if it's for it to be split evenly into two nucleons, this is not as likely. Note that this distribution does level out as we increase the energy of our incident neutron. That's what these two lines mean, where we have our thermal, those low energy neutrons, which could be produced by a variety of sources, or fast neutrons. This is 14 MeV, which is well above that 1 MeV threshold for fast neutron. Also note that for these fission reactions, as discussed before, we have a number of neutrons as well as gammas that are produced by this reaction. So here we have 3 neutrons that are produced by this fission. However, these neutrons, this could be 2, this could be 1, this could be many. It will vary by the specific event. So I saw a chat in question asking about attenuation, and the nice thing is we'll be going over that pretty quickly. So as I've talked before, we have different interactions. So I've talked more briefly about cross sections, where the cross section is our probability of interaction between our particle and another medium. Here we have a cross section versus energy for a neutron and here we have our 3 different regions. We have our 1/v region, which our cross section is dependent loosely on the inversely related to the energy of our neutron. And we have the region of harmonics, which are from this region between around 1 eV to around 1 MeV. And then we have the fast neutron region immediately after this. Here is another one of those cross sections. This is for cadmium, and this is where we get that definition of our thermal neutrons. So here we have this peak right here, which corresponds to that 0.025 0.025 electron volts. So here we have a increase of probability of capture of these neutrons on cadmium, followed by a decrease of this probability into our harmonics as we increase in our incident energy. So this is where we get that thermal energy definition. So interaction probability. So also note that it has a very odd, I thought this was always odd when I first got into this, but our cross section is given by centimeters squared, and it's given by Barnes, which is 10 raised to the negative 24 centimeters squared here. So it also, so whenever we have our material, we can have different cross sections of interaction. We can have cross sections of our scatter reactions, as well as cross sections of absorption reactions, and we could split those down even further. We have for elastic, inelastic, neutron absorption, or fission reactions. And we can define a probability of a specific interaction by the cross-section of that interaction divided by the total cross-section. Note that all these cross-sections will vary very greatly by the specific material and specific energy. Yes, so I got a question talking about the specific harmonics. So those harmonics correspond to different quantum states that the nucleus can take whenever absorbing that neutron. And that's as much as I can really comment on that. As the rest of it's more of a quantum physics question. So one way we can use these cross sections is we can make this idea of a microscopic cross section, sigma, lowercase sigma, and convert it to our macroscopic cross section, which is capital sigma, which just describes it's a quantity that describes the likelihood of a specific interaction for all nuclei in a given volume. So here we get this value by multiplying our sigma or microscopic cross section by the number density of our material. And here we have a better idea of interactions based upon the material we're actually using. So here, as someone asked in the chat earlier, we can talk about attenuation of these beams of neutrons. So I here is our intensity of like our neutron source, and I naught is the initial intensity, and I with no subscript is our final intensity. We can give this can be given by E raised to the power of our macroscopic cross-section multiplied by our thickness. Or we can express this in terms of our microscopic cross-section times our by our number density, or we can have the reciprocal of this macroscopic cross-section is our mean free path within the material. So Here we have another practice problem where we can go over our attenuation. So if we were to have our thermal neutron of around 0.025 electron volts, and it's incident on a uranium metal slab. So we have different cross sections that correspond to both our fission as well as our total interaction cross section. So from this, we can calculate our distance for the neutron to travel before any interaction is going to take place. So on the bottom of this is just a description of how you would calculate that density or molar density for atoms per centimeters cubed. Here we have the density of uranium, which is 19.1 grams per centimeters cubed, which is pretty dense. For reference, water is around 1 grams per centimeters cubed. It's multiplied by Avogadro's number to get our atoms per mole, and it's divided by the total the mass of our uranium in terms of grams per mole. And from this, we get 4.9 times 10 to this 22nd atoms per centimeters cubed. So given these values and this equation, you can calculate that average distance for neutron travel before the interactions of fission or any interactions at all. So I can give you guys 5 minutes to go through this, and I can also work through the different problems in chat. Yeah, so for the calculation of the cross sections, so those I'm not too well versed in the actual calculation of these cross sections, but I believe that that question can be better answered by those who are giving talks later in the summer, who will be discussing simulation. So that if you're to tune for those talks, they'll be much more knowledgeable and give a great explanation on that. And for cross section and the de Broglie wavelength, I would say not really, not in this situation.
I'll say it depends on the energy of the neutron, which is like components of de Broglie wavelength. So like, kind of, but like it's energy.
There's also a question on how do neutron scattering techniques contribute to our understanding of the structure and dynamics of materials at the atomic and molecular level. So for that, well, it's helpful as it's helpful in as we're able to interact reliably with um, the atom or the nucleus itself. However, for our applications, we're more so interested in the neutrons that are produced, or the neutrons, more so interested on the reverse side of that, understanding the neutrons as opposed to the materials that the neutrons are incident on. And how do we know how much target nuclei exist within a material? Well, from that we can do, other people can work through, like material scientists can work on and get a better idea of an actual density calculations through different TEM or transmission electron microscope experiments where they can understand like the crystal structure of a material, and from that you can get a atomic density pretty reliably. But for our methods, we can simply do our density calculations, which would, if we were to have like a rectangular brick, we can just calculate that by ruler and a scale. All right, I'm going to go ahead and work through the solution so we can have some more time for Q&A at the end. So given that our density for atoms per centimeters cubed, we can plug that in or multiply that by the different cross sections here. We have multiply it for our total cross section to get that microscopic cross section, as well as our cross section for fission. And now we have 33.8 inverse centimeters and 28.5 inverse centimeters for fission. From here, we can then calculate our mean free path by simply taking the reciprocal of this value. And now we get 0.03 centimeters. So our neutron on average will travel 0.03 centimeters before having any interaction, or 0.035 centimeters before undergoing fission. So from here, I'm just going to give this acknowledgements to the MTV for helping fund all of this work that's done at these labs in different universities, as well as our fair use disclaimer, as well as some other resources for those who are curious about a few more things in here. So here we have the Lambda Pando manual, which gives us information on how these concepts on neutron scattering and all these can be used for understanding different material and quantizing these. This will tie in directly with tomorrow's talk with Carrie Ann. We also have Null, which is a very helpful textbook about all things radiation detection, as well as these two other sources here for NIST and APS. So I can now take questions.
Yeah, thank you so much, Ethan. That was an awesome talk. So I think we should get started addressing some of the questions. So the first question we have is, are thermal neutrons called thermal because they get their energy from ambient heat?
Yeah, so not really. Thermal, it's more so they're thermal regardless of where they get their energy from. We usually get neutrons as they bounce. If we have a high energy neutron, it will slowly lose energy as it collides with different atoms in the environment. So if we were to in a perfect scenario, if we're doing a measurement, we just have our neutron source and our neutrons interact with our detector, and that's all that there is. However, in the real world, those neutrons will be bouncing all across the room. They'll be depositing little bits of their energy as they move along. And because of that, we'll have neutrons in the environment that are in this lower energy region. But it's, yeah.
Yeah, that's great. And then it's also called thermal because the kinetic energy of the neutron is in thermal equilibrium with the room. All right, and then the next question, can you explain slide 4 again?
Yes, was there any particular part of slide 4 or just a brief rundown again? Or so we were talking about.
Yeah, maybe give some specific examples of neutron sources as well. I saw a question about that earlier too.
Yeah, so for slide 4 first, we were just discussing on whenever we have this is just talking about how our average binding energy. So for, let's say for helium-3 or like helium-4, we need our atom to be around an excited state around 7 MeV for it to even consider releasing a neutron into some process of that gamma ray. So these energies are simply too high for us to usually get that. And the different neutron sources in the reactor. So we can, in our reactor, we can have a variety of neutron sources. I'm actually not sure of what specific neutron sources are used currently for those to begin those reactions. Karen, if you want to comment on that, if you know. If not, I can get back to you on that.
Yeah, I can jump in. So I know for the first reactor ever, they used a radium beryllium source. But I guess you could also like probably use spontaneous fission sources like californium or something like that. If you like remove it from the reactor. But that's just to get the chain reaction started.
And once that's done, it should be self-staining.
Okay, so this question says, are there any methods available for direct neutron detection that do not rely on indirect processes or require the thermalization of neutrons?
Yes, I will be brief on that explanation because Carrie will be talking all about this tomorrow within her talk. So we can have some it we have we have detectors called scintillators which interact with both the it's I'm not sure if it fully fits into that category you lined up because it fits so it will neutrons can interact with our scintillators and produce light, which we read out by a photomultiplier tube, which converts that light into a voltage pulse. And using these different scintillators, if it's neutron sensitive, we can differentiate between neutrons and gammas based on those pulse shapes. So it's not just helium-3 detectors and lithium-6 detectors. Yes, and someone asked to share those links in chat. I could put those in. Sorry, it's not letting me. If I click on them, they'll just take me to those sites. So this will be shared online in the form of a YouTube video that you can access through the MT website, and you can access those links from there.
All right, so this question says, why do DD reactions form helium-3 and a neutron rather than helium-4, since helium-4 is stable?
I'm I'm not sure the particulars of the why the helium-3 is produced as opposed to a simple helium-4. I would presume that it's the neutron is released to de-excite the atom or the nucleus. That's the reason why it doesn't produce helium-4.
Yeah, just the bottom line of this is cross sections. But I'm not super familiar with the mechanics that make up these cross sections or like why these cross sections are the way they are.
So there's a question on, does fission reactions occur when only neutrons have lower energy? It's not only, but they have a higher cross section for that reaction at that point. That's kind of how a lot of things are. It's a lot of reactions can occur at a variety of energies, but in most cases, that cross section in most cases is too low. It's many cases is negligible at different energies. And the fundamental difference in terms of interactions in alpha emissions and neutron emission, I'm not quite sure what you mean by that question, if you could rephrase that. Oh, so there was a question about protecting ourselves from free neutrons. So that one's more of a, yeah, so with that, within a facility, you have to be careful on shielding and keeping yourself safe in those situations. So we can do that by different shielding. We use borated poly or materials with that low Z value to scatter those neutrons. And to make sure that we're safe in those scenarios, we can use various detectors to measure the neutrons produced by source and make sure that where we're at in the lab is safe. So yeah.
All right, and then here's a question. How do we calculate neutron cross sections at specific energies for any arbitrary material computationally? Could you suggest free computational tools?
I know I cannot, but I know, so we have a pretty great professor who should be giving a talk, Dr. Krajewski, who will, I know he has, he should have materials for this as he gives talks, well, he gives classes on the actual computation of these cross sections. So he should be in the MCMP simulation week, and I'd highly recommend attending that as he's a pretty great lecturer.
Yeah, if you just need to pull a cross section out of somewhere for one energy, like if you just want like the thermal cross section for uranium-235, you can go to Janus. That's like my preferred website to do that at. But all right, this question says explain the relationship between neutrons and K multiplication factor. Ethan, I can take this question if you would prefer, since I have a nuclear engineering background, but if you got it, you can do it too.
Yeah, I'm not sure on the context of the K multiplication factor, so you can go ahead.
Okay, so this is definitely more of a nuclear reactor question than a radiation detection question, which is kind of like what Ethan and I specialize in our group here at the University of Michigan. But the K effective, or the multiplication factor, is a ratio of the number of neutrons in one generation compared to the number of neutrons in another generation. Right, so like if you have one neutron induced fission and two neutrons are produced, then the multiplication factor or the K effective would be 2. This depends on a lot of things. It depends on volume, leakage, like all like it can be pretty in depth. But essentially for a reactor to be critical, K needs to be 1. If it's above 1, then it's super critical. So, yeah, hopefully that was helpful.
I think at that we are just out of time. Thank you everyone for coming in for the talk.
Yeah, thank you so much, Ethan. That was a great talk. Feel free to join us tomorrow and we'll talk about neutron detection. So thank you, everyone.